Yeah, welcome back to this third lecture on probabilistic programs and how we can verify them. Okay, yeah, so this is kind of sort of where we are. We're on day 3. We're actually going to kind of continue talking about this weakest pre-expectation calculus that I started last time. And yeah, like I said, please ask questions. Brendan here will moderate, and I've figured out how to use the chat window on the same screen so I can actually see some of the messages now too. Okay, cool. So last time we spent most of the time talking about this semantics for this probabilistic imperative language PWHILE. This is what I call the monadic semantics. So if you remember, this semantics had this following kind of type, where the meaning of a command mapped a single memory to a distribution on memories. Okay. And last time we started talking about this weakest pre-expectations thing. The main idea is that given kind of a PWHILE program and a post expectation, I'm going to call it E. This maps each memory to a real number. We want to kind of compute weakest pre-expectation of C and E. And this is again going to be an expectation that is going to map every input memory M to the expected value of the expectation in the output of the program C, if you run C on the input memory M. Okay, so it's a little bit convoluted. We also talked a little bit about, what this might be useful for, like why would you want to kind of compute the expected value of something in the distribution? Well, many kind of probabilistic properties you might want to analyze can be coded using different kinds of expectations, right? So if you want to figure out what is the probability that X is equal to Y in the output distribution, I want to show this is 1/2. I can encode this as an expectation and then try to compute the WPE. Maybe I want to compute the expected value of the running time T in the output, and I want to show it's equal to like N plus 42, where N is some part of the input. I can again encode this as an expectation and then try to compute the WPE. Okay, cool. So, right, so last time we kind of were talking about how to make computing this thing easier. We want to kind of define this a way to compute this thing so that you compute it based on computing WPE for the subprograms. So you can break down a complicated computation into simpler parts. So we were doing with skip last time. Just remember the program is going to be skip. Post expectation is E. And then the average value of E afterwards is just the value of E before. So we can define WPE of skip and E is just E. Right? This says that if you want to figure out what is the expected value of E in the output distribution, that is just going to be evaluating E on the input memory. Because the skip command doesn't actually do anything, doesn't change anything. Likewise, we had just talked about for assignment. Here the program like assigns an expression to X, and then you again want to compute the WPE of a program and an expectation E. And like you can kind of compute it using this formula, which is very similar to what you have for kind of the weakest preconditions kind of thing for Dexter's weakest preconditions. Okay, so I just want to quickly go through the other kind of commands to show you how you compute WPE. So maybe the most interesting command you want to see is for random sampling, right? So this is one thing that is not in the standard imperative language we talked about last time, where you want to sample something from a distribution and store it into variable X. So here, the post expectation is, let's say it's E, and you want to figure out what is the average value of E computed in the output distribution after running this sampling command, right? So kind of intuitively, the average value of E is going to be, you're going to look at every single possible value of X, which is the sample value. You're going to say, oh, the first possible value of X has this probability and then leads to this expectation. The second possible sample value of X has this other probability and leads to this second expectation. So kind of you want to take like a weighted average of this expectation E over the different possible results you get from sampling X out of D. Okay. So a bit in like say in mathematics, you can say that we can define WP to be like this. So here I'm going to say this is for the biased coin flip. Again, remember that this thing returns true with probability P and false with probability 1 minus P. And I'm going to say that the weakest pre-expectation is going to be defined to be the weighted combination on the right, right? So with probability P, I want to compute E where x is replaced by true. And I'm going to add to that with probability 1 minus p, I'm going to compute e with x maps to false. So I kind of said with probability, but I really mean this is a kind of like an average. Like this is a weighted average. With probability p, you see e with x mapping to true. Otherwise, you'll see e with x mapping to false. Okay, and you can extend this to other primitive distributions, like rolling a dice or like a fair coin flip. If you're curious, you can kind of try to just generalize this and define this for other distributions. Okay, but it's all the same idea where you want to take a weighted average. Questions so far about this?
I don't see any in the chat, but maybe I could ask like a high level
Sure.
question, strategic, where we're going with this. I'm curious if this WPE calculus is related at all to like error bounds tracking or significance figure arithmetic, or maybe there's a way of keeping track of not just the expectation, but maybe the variance and other values. Is this kind of analogous to those algebras or calculi?
It's a good question. So I think this is kind of a very general technique that you can use to compute various kinds of averages. Okay, so a variance is also a kind of average. So you can encode variance using an expectation and as an average. So if you wanted to compute something about the variance of some quantity in the output distribution, you could do that by encoding it as an expectation, then trying to compute the WPE. So kind of as I've presented here and as it was originally kind of imagined, this weakest pre-expectation is not really application specific, right? It's not for tracking error or accuracy or running time or anything else. Just like Dijkstra's weakest precondition was not, for any purpose, right? It's just saying any kind of assertion you give, we can try to compute the WP, right? So here, this is kind of, intended to be a very general tool that you could use for many purposes. You would have to find like the right kind of expectation to instantiate here. But once you do that, like in principle, you could try to compute this thing, and that will give you maybe some information about the distribution that you care about for your application. Yeah.
Okay, thank you.
Someone raising their hand?
Thank you. Yeah, I was wondering if I understand this correctly. It seems to me that you can mostly like model this weakest pre-expectation as a weakest a precondition if you just say that the expectation, the proposition being that the expectation is equal to the value you're looking for. Do you understand what I mean?
Right. It's a good question, right? So it's a good idea. I think there are maybe two things that are maybe not so clear with this, now how to set this up, right? So the first thing is that, for weakest precondition, the language does not support random sampling, right? So you would have to define weakest precondition for a language with random sampling, and this is going beyond what in Dijkstra's weakest preconditions. The second thing is that you're kind of saying that maybe I can encode like expected value as saying like the expected value is going to be equal to this concrete value like 1/2, and I want to treat that as a assertion, like a binary assertion, and then compute the weakest precondition. So using Dijkstra's weakest precondition. So I think in general you won't know like what that expectation is going to be a priori, right? Like if you already knew that the expected value would be like 1/2, or you had then your task would be a little bit easier, I think. So I think there are a few things that make this not so easy to exactly just apply Dijkstra's weakest preconditions for this. It looks syntactically very similar, but I do think it's kind of its own thing.
Yeah, I suppose it also breaks apart once you like start adding the expectations. You couldn't do that in the same way with the post conditions or preconditions.
Sure.
All right.
Okay, so I'm going to continue to show a few more cases to give you an idea how this thing works. So sequencing, program is sequencing in two programs. I'm just going to kind of jump ahead and say that this works exactly the same thing as Dijkstra's weakest preconditions, where the WP of a sequencing is just the composition of the WP of two things, right? So you first compute the WP with respect to the second program, this bit here, and then you get some expectation. And then you compute the WP with respect to the first program, and you get some other expectation. Okay. Again, this is a very, very clean formula, so it makes it really easy to deal with kind of sequential composition. Just kind of compute the WPE backwards. It's maybe worth, if you have some time and you want to look into this, try to unpack exactly why this is true. So it's starting to become less clear why this is true, but it's also not too hard to show that this does hold and it does compute the right thing. But again, it syntactically looks very, very clean. Okay, so for conditionals, if you remember way back the last time, for conditionals for Dexter's weakest preconditions, we had this kind of two cases where he said, like, if the guard was true, then you compute the WP of the first branch. Otherwise, if the guard is false, you compute the WP of the second branch. Okay. And again, here you can do something quite similar. Right. So here, just the notation is now kind of different. So to kind of read this bit here, let's say what is the expected value of E after running an if then else? Right. Well, if the initial value, in the initial memory the guard is true, then this is 1, and I'm gonna just compute the expected value of E after running C1. Otherwise, if in the initial memory the guard is false, then this part is 0, and this second thing is 1, and then I'm going to compute the expected value of running the second branch. Okay. So in some sense, kind of using this indicator function times something plus indicator function times something else, this is kind of simulating the role of kind of this if then else thing we had last time, where if something is true, then you do this, else if something is false, you do this other thing, right? Like it just happens that in these two kind of things that are being summed up, at most one is going to be 0, right? So one is going to be 0, the one that corresponds to the false branch, and one of them is going to be non-zero, potentially, the one that corresponds to the branch that is taken. Okay. Any questions about this, the conditional rule? So it's still looking sort of similar to Dexter's weakest preconditions. You can read it in a similar way, but it means something quite different. Cool.
There's a question. It's kind of a technical question in the chat. Maybe you want to save that for later. But I'm kind of curious for this conditional rule. Is there a way to express this in terms of the convex combination you described the other day? So, like, if you had the distributions, functions of the distributions you care about in each of these branches, could you merge them? The second or the first order rule using a functional approach as well, just out of curiosity.
Right. So I think here we would not want to merge it using convex combination. So this is a good question. So like convex combination, you would like to merge two things if there's some probability of taking the first branch and some probability of taking the second branch. But if you remember, like all of this that we were building here is based on this monadic semantics, where the initial thing into your command is always a single memory. So in that single memory, either the first branch is taken or the second branch is taken. There's no like probability of taking the first thing or the second thing. You either take branch 1 or branch 2. So I think I might talk about this a little bit later, but all of this weakest pre-expectation stuff is really matched to the semantics we chose, this monadic semantics. So if you took a different semantics where the input to a command was a distribution over memories, then a lot of this stuff would need to be adjusted. And I'm actually not sure off the top of my head what this WP stuff would even look like anymore, right? Because like for conditionals, it wouldn't compute the right thing anymore, right? Because it's not true that from the initial input, you either take the first branch or the second branch. You might take both of them with some probability. But that's not the case in the monadic semantics we've taken so far. It's a good question.
Thank you.
Okay, cool. So let's see. So this is the main soundness theorem for WP. So, I was a little bit confusing and said like, I defined WP to be this way or to be that way. But this is, as we've done so far, we've defined WP via the equations I just showed before. And now you want to prove something like this, right? So this says that if I have a program C and an expectation E, and I compute the WPE, then if I plug in a memory M, I'm going to get out some number, right? And this number is going to be precisely the expected value of E on the output distribution of C, where I've gotten the output distribution by running C on M. So M is kind of the input memory to the program. I'm saying if you evaluate the weakest pre-expectation on M directly, you will get the same thing as if you ran the program on M and then averaged E over the output distribution. Okay. Okay, so, this kind of this is something that, if you're curious, you can try to prove at home. It's really not that bad, especially for loop-free programs. I haven't talked about loops at all. For loop-free programs, you can do this by induction on the program structure and just unfold the definition of the semantics, unfold the definition of expected value, and just kind of crank through this. It's really not bad. And right. Okay. So this is the main thing that we want to show for WP. This says that kind of the WP is computing something that means what we think it should mean. Okay. So I'm going to kind of move next to talking about loops. Again, I'm going to be kind of sketchy here because things get rather strange, rather more technical. But I was going to show a few warm-up examples of trying to guess the WPE, right? So let's say this is the program here. It says n is 100, and while n is bigger than 42, we're going to decrease n by 1, right? So the post expectation is going to be just n, right? So this program is not even probabilistic. But I can still compute the WPE for this thing. And what do we think this should be? Looking at the chat, sorry, not looking at the chat. 42, excellent, right. So why is it 42? Well, we want to find the expected value of n in the output distribution. So since the output distribution is just one memory now, it has all probability on one memory, we want to figure out what is the value of n in the output. And in the output, the value of n is going to be exactly equal to 42. Because starting at 100, and as soon as you kind of reach a point where it's greater than or equal to 42, you stop the loop and you finish the program, right? Great. Okay. So, we can make more complicated programs and it may become slightly harder to see, what's going on. So here's a little different of a program where my program has the same behavior kind of, but now I'm not going to decrease n by 1 every time, right? I'm going to flip a fair coin, and say if it's true, I'm going to decrease. Otherwise, if it's false, I'm not going to do anything. Okay. Any guesses about what the WP should be now? I should have made a different thing because I can't even tell if these are new answers or old answers. But the answer is that this one should still be 42, actually. Right, so it's a randomized program, but it always terminates in a state where n is equal to 42. So if you find the expected value of n in the output distribution, you're still going to get 42. Okay. Things start getting more complicated. We can make more complicated things, and it may be harder and harder to figure out what is this thing supposed to be anymore. Again, we have a very similar situation as for the standard deterministic programs, where we can define WP for loops mathematically, but it's hard to compute, right? So it's defined in terms of a least fixed point, and it's hard to kind of compute this thing directly in terms of WP of the body. So this is what we actually want to do is the body of the loop is going to be simpler than the loop. So we would like to compute WP on the body and then transform that somehow to make the WP of the whole loop. That would make our task easier. But it's hard to do this because of how WP is defined for loops, which I kind of won't cover here. But we're going to use the same kind of trick that we use for dexterous weakest preconditions and just say, we don't have to compute WP directly, right? So, for dexterous weakest preconditions, we said maybe we just want to show that there's an implication, right? Something implies a WP. So here, we don't really have implication anymore because these are not logical predicates anymore. You can't say one expectation implies another one. But we might want to do something similar where we say we don't want to compute WP exactly. I just want to find like an upper bound on WPE or a lower bound on WPE. Okay, so I want to find an upper bound on expected value or a lower bound on expected value, and that might give me enough information already to establish what I want to show. Okay, because computing this expected value exactly can be very difficult. Okay, so there's at least two rules that we can use here. So one is called the super-invariant rule. This is the one I'll talk about first. So this one is to find upper bounds on WPE. Okay, so I'm given a program, a loop, while E do C. I'm given a pre-expectation now, I'm gonna call E prime, and a post-expectation E as before. And my goal is to check this inequality. So I want to check that E prime is bigger than the WPE of the loop and E. Okay, so that's what I want to check. If I can compute the left side exactly, then this wouldn't be very difficult. But I want to do this, without computing the left side exactly, because that's difficult. So the super-invariant rule says that you can prove this inequality here, this upper bound, if you establish kind of two things. So again, you have to find some expectation I, which is I'm going to call the invariant, and it should satisfy these two super-invariant conditions, right? So I should be less than E prime, which is the pre-expectation. And again, I have this kind of thing here where somehow I is bigger than the WPE of I itself somehow. So if you remember from the weakest preconditions, we had kind of three conditions. This second condition here is really kind of an if then else again. So you have the same pattern where you have indicator of E times something plus indicator of not E times something. So this kind of merges together two of the cases in the weakest preconditions we had before. But the upshot of checking these two things is that if you can check these two things and an expectation I, the invariant, then you can conclude this, which is what we wanted to conclude. Okay. So it's, again, you have the usual trade-off, like it's hard to find this expectation I, but if you can find it, then checking these two conditions is much easier, right? Because here, this is just a WP of the body. So the body is going to be simpler than the whole loop. The body might have other loops in it, but then if it does, you can just check, you can apply this rule again and try to, analyze the loops inside C as well. So we've essentially kind of eliminated the loop from the reasoning. We don't have to think about the loop anymore, or WP of a loop. We just have to think about the WP of the body and this first condition, which is easier to check, and finding this invariant I. Okay, so this is the super-invariant rule. Any questions about this so far? I'm going to talk about a variant of the rule next.
The first question from Takaram Golamudi asks, why does the previous while loop terminate? And are we using the central value theorem to conclude that?
Right, so it's a good question. I kind of glossed over that. I just kind of asserted that it is going to terminate. It is going to terminate. So there's a lot of research on trying to understand how to prove termination of probabilistic programs. So I'm mostly not going to talk about that in these lectures because there's too much stuff. But one of the conditions that is sufficient, but not necessary, is that you have a decreasing variant, something that is going to decrease and bounded below by 0. And the variant decreases with constant probability, with at least constant probability. So with at least constant probability, you will decrease constant bigger than 0, right? And this is known to be sufficient to prove termination. Yeah.
Okay, and Krishnamurthy asks, is this like the method of conditional expectations? I don't know what that means.
I don't know of an exact connection there. Yeah, so I don't know an exact connection there, but maybe.
Okay. Yeah.
So this is for those of you who maybe know more about probabilistic processes. I think one way to think about this kind of condition is as kind of a martingale condition. So this is, you can show that I is kind of like a martingale, and this kind of, the soundness of this rule looks something like the optional stopping theorem. But if you don't know anything about this, or like a super martingale, but if you don't know anything about this, that's also totally fine. You can just take this exactly as a variant of, it's like an invariant rule that's kind of like the loop invariant rule we have for Dexter's weakest preconditions, but adapted to this weird setting of expectations. Okay, sub-invariant rule is almost the same thing. So the difference now, oops, I'm missing an inequality here. The difference now is that we want to check if E prime is less than WPE. Okay, so the previous rule gave you ways to show that WP is less than something. Now I want to give you a way to show that WP is greater than something, at least something. Okay, so again, that you have to find this I. Let me see if yeah. So if you kind of look, the direction of inequality has swapped pretty much in the two rules. The only extra condition here is that we need I to be also bounded in 0, 1. So this is for some technical reasons related to termination, but I must be bounded in 0, 1. And once you have that, you can check these two conditions, and then you will prove a lower bound on the WPE. Okay, so this is the sub-invariant rule. It's sub because invariant is less than, somehow less than, I is less than this thing. So, okay, great. So, okay, so we have these two rules. They let us prove upper and lower bounds on the WPE of a loop. Of course, the big catch is you have to find an expectation I, and that may be difficult, right? You have to just magic this out of nowhere, just like for finding a loop invariant, pretty much. Okay, so I want to show a really quick example of how this works. So the example I'm going to consider is a program I call FAIR. So the idea is that you can simulate a fair coin flip from biased coin flips, right? So the idea is that here, someone has given you a biased coin, maybe it's 1/4 true and 3/4 false, and they want you to produce a fair coin flip using just this thing. So you're not allowed to flip a fair coin. You only have this weird coin that, is not 50-50, and you want to use it somehow to make a fair coin flip, like a fair Boolean. So here's kind of one known way to do it. It's kind of cute if you have seen this before. So the idea is that you start with x and y being equal. So you go into the loop and you flip the kind of weird coin twice, right? So you have x and y, and as long as they are equal, you get equal results, you continue trying, right? But as soon as you get two different results, you just return, you look at the value of x, and that's going to be a fair coin flip. The rough idea why this works is that when you exit the loop, you're either going to have x to be true and y to be false, or you're going to have x to be false and y to be true, because they're not equal. And both of these alternatives have equal probability. Okay, so they either, you have 50-50, you see the true first, and that's why you stop, or you see the false first, and that's why you stop. But those are equal. Okay, and this works even if this is a biased coin flip. It doesn't have to be a fair coin flip. Okay, so the goal, I want to show that, if x and y are equal initially, then the final x is a fair coin. So in terms of WP, I can try to prove this equality here, right? So what does this say? This says the expected value of, sorry, this should be an indicator x here. Sorry, indicator x here. The expected value of indicator x here is a probability that x is equal to true, right? So I'm going to say that is going to be equal to 0.5 if x is equal to y, or it's going to be equal to just the initial value of x if x is not equal to y. Okay, so this is stronger than I need to prove. So I really only care about this bit here, which says that if x is equal to y initially, then the expected value of indicator x is a half. That's what I actually care about, because that says that the probability of getting true at the end of the loop, x equals true, is going to be 1/2. Okay, so, but again, fair is a loop, so I can't directly compute the WPE of this thing. So we're going to prove this in 2 steps. I'm going to prove the kind of an upper bound and a lower bound, right? So I'm going to prove inequality at the end of the day, but I'm going to prove kind of 2 inequalities, so one in each direction. Sorry, that should be x also here. It's a typo. Okay. So let's try to prove the upper bound first. So we want to find an I satisfying the super-invariant condition. Which is this thing right here. Okay. So the other condition is maybe not so hard to show. So I'm just going to take the desired thing here to be the invariant. I is going to be just this thing. This is kind of, if you remember, this is kind of the thing I claim the WP of the whole loop is equal to. And in this case, it is also an invariant as well. So here you can go through this kind of tedious calculation here. It's not too interesting, but essentially I can kind of apply the WPE calculus rules that I showed before to kind of compute this, this thing. So this is just a bunch of stuff. You can go through this if you're curious, you ignore the stuff if you're not curious. But upshot is that the thing on the left, the first thing is less than the invariant I. So that's the thing I needed to show in order to show that I is a super-invariant. Okay, the rest of this stuff just follows by kind of applying WPE of sampling and of sequencing, pretty much. Okay, just unfolding the definition and substituting stuff in, canceling stuff that's 0, and so on. Okay, it's not really interesting. It's just some algebraic manipulation. Okay, so since I have this, the super-invariant rule will prove this upper bound. Okay, that WPE of the fair program with post expectation x is at most this thing on the right. Now the sub-invariant rule is almost the same. So this shows a lower bound. Again, I'm going to choose I to be just the same invariant actually. And you can see that I is going to be bounded in 0, 1. So it's if this is true, then I is at most a half. If the other thing is true, then I is at most 1. So it's bounded in 0, 1. And again, doing that kind of boring calculation I showed before, you can show that you have a sub-invariant rule that proves a lower bound. I think it should be sub-invariant, not super-invariant. Sorry, more typos than usual. Okay. Yeah, so this is a really quick thing. I didn't really want to go through all of this. I really promise you that this is really just applying the definition of WP we saw before and just substituting in stuff and canceling stuff that's 0 and just moving stuff around. There's not anything really interesting happening here. Once you have an invariant, this is easy to check. Okay, cool. So I think that's pretty much all I want to talk about for WPE. Some references and for the reading, I think the best reference I know of is this recent kind of thesis by Benjamin Kaminsky. I really recommend it. It has a lot of interesting stuff on kind of recent developments of this kind of calculus, trying to use it for proving expected running time, for proving conditional probabilities and things like this. But there's also a really good, solid third of the thesis in the beginning where he just goes over things very slowly and try to synthesize a lot of the literature on this stuff in a uniform manner and starting from completely the basics. There's of course also this comprehensive book by MacIver Morgan. This is a very large book summarizing a lot of their work in the last, many decades on this stuff. But you can look into it if you're curious. Okay.
I think there was a question, just a quick question about the equations in the previous slide. Why do we need I to be in the unit interval, Alex asks, for sub-invariants?
Yeah, so I think this I think is better explained in Benjamin Kaminsky's thesis, but this condition is needed. Somehow proving lower bounds on the WP is more difficult than proving upper bounds. Somehow I think because when you prove a lower bound, you have to somehow also ensure that the program terminates sufficiently often somehow. So yeah, off the top of my head, I don't have a counterexample that for why you need to be bounded. But this is one kind of subtle aspect of WP, some strange aspect. Yeah, I think there's some counterexamples where if it's not bounded, then then the rule is not sound. The sub-invariant rule. The super one does not need this kind of condition. And also throughout everything all the expectations are assumed to be non-negative. Again, there can be some weird examples. So there's some, I think, recent papers showing extending this kind of thing for mixed sign expectation, and it's more subtle because more strange stuff can happen. Yeah. The questions?
I don't see any.
Okay, cool. Let's continue. Okay, a lot of this stuff is related to kind of Hoare logics for probabilistic programs. Here are some references for various systems that I and other people have worked on in this area. But I'm gonna kind of skip over this stuff for lack of time, let's say. Okay, so far we've seen the monadic semantics, the first semantics, and we saw WPE, which is one way of reasoning about PWHILE programs. So here I want to start presenting another semantics for PWHILE. You might wonder, why a second semantics, and I think there's at least a few good reasons. I think one reason is to give us an alternative view of what the program does, right? So you have a program on, you wrote down in some text. There might be various ways of viewing how this program executes. What are the inputs? What are the outputs of the program? How does it compute, right? And these models will have different correspondence with reality. Some of them will be more faithful, some of them will be less faithful. Another reason to consider other semantics is that they might enable different extensions of the language, right? So you might want to extend the language PWHILE with other features, and for that you might need a different semantics because to interpret the new command, understand what does the new command mean mathematically, we might need a different kind of semantics. And I think the thing that's most important for the purpose of this course is that a different semantics can support different kinds of verification methods, right? So changing the semantics might make certain properties easier or harder to verify. So depending on what kind of property you're verifying, you might want to change the semantics or pick a semantics that is more suited, kind of proving what you want to prove. Because it's not the same, it's not like all properties are equally easy to verify under all semantics. This can have a big effect. Okay, so I'm going to kind of step into this second thing, just kind of jumping in. We're going to define what's called the transformer semantics for programs. So for expressions and distribution expressions, everything is unchanged. Okay, so I'm just going to skip over this. Everything is completely unchanged. Interpret expression in a single memory, and it'll give you a value. Okay, and distribution expression, again, you interpret as a mathematical distribution over values. Excuse me. So last time was all the monadic semantics. This time we'll see the transformer semantics. So I'm using a different notation here where I have these square brackets around the command C now. And the only difference is that unlike the previous semantics, the input to the program is now going to be a distribution over memories. So this bit here is different. Okay, so this kind of semantics was first developed by Dexter Kozin, one of the first papers about probabilistic semantics. It's also interesting and allows different kinds of verification techniques. Okay, so that's the only difference, is that the input to the program is now a distribution over memories. Okay, so I'm going to quickly step through, the different commands. Most of them are kind of boring. So for skip, I have input is a memory distribution now. I'm going to call it mu, and the output is clearly just going to be the same memory distribution mu. Right, so remember before, for the monadic semantics, I had to do some stuff where I had like this unit and return stuff to convert a memory into a distribution. Here, I don't have to do that because the input is just a distribution already, and the output is a distribution. I don't have to wrap a memory into a distribution because it already is a distribution. For assignments, here's kind of the intuition. So again, I have a memory distribution, that's the input. And the output is going to be the distribution that I get from sampling m from mu and then mapping m to have x updated with v, where v is the original value of e and m. Okay, so I sample a memory, I look at what is the value of the expression e in this memory, and then I change this memory to be updated so that x holds v. Okay, and that's going to give me an output distribution. So we can kind of accomplish this using this mapping construction we saw before. And so I'm going to find this mapping function that says, f of m, f of a memory, is going to take a memory to an updated memory where x maps to the value of e and m. Okay, so this little bit here. Okay, this is essentially this is the semantics for like assignment command in a deterministic language. Okay, and now we can lift that to the probabilistic language by saying if I have input distribution over memories, I just map this function f over mu. Okay, so f takes memory to memory. Mu is a distribution over memory, and when I map f over it, I'll get another distribution over memories. Okay. Questions so far?
Prasanth asks, how is the output of a distribution, even though we sampled m and updated it? I'm not sure, I didn't really parse that, but how is the output, how is the output of distribution, even though we sampled m and updated it?
How is output distribution? Right, so I think, yeah, so my intuition here is maybe not super clear. I sample m from mu and I mapped it to be something else, but the result is not going to be just a single memory, right? So I kind of imagine I have a distribution of memories and I sample something from it and I map across to a new memory, but now I have a resulting distribution on output memories. Maybe thinking about it in terms of the map function is a little bit easier. Not quite sure. This operational one of doing some sampling and then doing something is maybe not so clear. But one way to think about this also is that no matter what I do, the output is going to be a distribution, right? Like I sample something, if I output m itself, I haven't somehow magically gotten rid of all the randomness, right? Like the m I output is going to be randomized because it came from some distribution. So there's an implicit distribution over the output as well. Cool. Okay, sampling. There's a few ways to kind of give the semantics for sampling. So one way is to kind of say, I'm going to sample a memory from the input distribution. I'm going to sample v from the d expression, which is the thing I'm sampling from. And then I output kind of returning updated memory m with x to v. Okay, so one way to do this is in terms of bind. There are other ways to do this in terms of kind of using the independent product I talked about before. This is kind of a mouthful here, but let me try to see if I can unpack what's going on here. So this says you bind by taking the input distribution mu, you grab some memory from it, and then you map this memory to this kind of ugly thing. This ugly thing essentially says, I'm going to map this function g of m over the distribution of values I sample from D. So this g of m thing kind of takes a memory and updates x to hold v. I'm going to map that over this D distribution, which is where I sampled the new value. And that whole thing there is going to be what is the result of the bind. Okay, so this is again, I'm going rather fast here. And I think this is kind of a mouthful to kind of look at all at once. If you kind of step through it like step by step, I think you should be able to see that the intuition I put above is kind of what you're doing here, right? So first you sample from the input distribution, then you take this memory, and then you map this memory. You map the value you got from the sampling the fresh value D. You map that value, you map the function g of m across this value to update the memory. And that's the final thing that you get. Again, there's different ways of setting this up. Another way of setting this up is to say, I first make this independent product of the input distribution mu and the D distribution, because I know that D is a fresh sample. Then I kind of sample from both of these things together and I combine them together into a memory. That's another way of doing this that would lead to the same kind of thing. Okay.
Krishna asks, if you roll a die and get even, then you output heads, otherwise tails. Is this what you mean kind of morally inside of this Cousins distributional semantics?
Sorry, I'm not quite sure I understand the question there.
Oh, maybe I should just read verbatim what he wrote. Maybe
yeah, I'm reading it right now. I'm not quite sure. I mean, Krishna, you can try to unmute if you think it's easier to ask your question.
All right, maybe I'm just missing something. It's possible. I'll just come at this later.
Okay.
Maybe.
Okay.
What I mean is, you're just essentially from one distribution, you're getting a new distribution, right?
Yes.
So this is an example of that, right? In the sense, you let's say you have a die, which can, a fair die, even if you have a fair die or an unfair die, you roll, if you say you get 2, 4, 6, and if I get a 2, I output a tails. If I get a 4 also, I output a tails. If I get a 6 also, I output a tails. Or sorry, I output in heads. And vice versa for the, so that's all you mean by transforming distributions, right, essentially?
Right, so that's one example of what a distribution transformer could do. Yes.
Right, yeah. No, I want a concrete example.
Sure.
Sure. Thanks.
Yeah, okay. Sampling sequencing. Sequencing here is actually fairly straightforward with the transformer kind of semantics, because I have some input distribution mu. I feed it through the first program, I'll get some, output distribution mu prime. I feed that through the next program, and I'll get some other final output distribution mu double prime. Okay, so the sequencing is just kind of direct sequencing, because you transform the memory distribution to another distribution to another one, and you feed it forward through your program. Okay, now I'm going to spend a bit of time talking about if then else. I'm not going to spend almost no time talking about loops. If then else is more interesting here now, right? So I'm going to try to present a few tries for how we can define the semantics. So let's suppose that the input is a distribution mu. So what can you do now, right? So the first problem we hit is that, what should the input to the branches be, right? So I have an if then else. I have an input memory, input distribution mu. I would like to run the two branches somehow, but there's I don't know what to actually feed into the branches, right? So, the first branch, it expects an input, whereas of the distribution where the guard is true. The second branch, it expects a distribution where the guard is false, right? But mu may have some probability of both cases, right? So you don't know that it's going to be 100% true or 100% false of the guard. Unlike the monadic semantics we showed before, you can't do a case analysis on the guard, or you can't just say it's either going to be true or false, and depending on that, figure out which branch to run. So what we're going to use this distribution conditioning operation that we saw on the very first day of class. Remember, if I can take a distribution, I can condition it by an event, which is a subset of the possible values. And this is going to be kind of the part of the distribution where the event is true. Okay, kind of reweight it so that it's still a distribution. Okay, so it's kind of the probability, it's the distribution assuming, something is true. So what we can do is we can say we have this input distribution. I can break this into two distributions where the first one is I assume that the guard is true, and what is the distribution there? And the second one is I assume the guard is false, and then what is the distribution there? So these will give me two kind of conditional distributions, which I can then feed into the two branches. Okay, so kind of that's what I've done here. I say I'm going to condition mu on the predicate guard is true, and I transform this conditional distribution with the first branch. Likewise, I can condition mu on guard is false, and I can transform this conditional distribution with the second branch. So now each branch is taking in a distribution where the guard is always true or where the guard is always false, okay, like it kind of expects in an if then else. Because you expect to run the first branch only on the part where the guard is true, not on the part where the guard is false. But now I kind of have two output distributions from the branches, but I need a single output distribution for the whole if then else, because I want to produce one output distribution, kind of not two of them, right? So for those of you that remember what we talked about before, like you may think that the right idea here is kind of combine these two distributions together. So what we want to do is we want to kind of mix these two output distributions together by using this convex combination operation I showed before. So the idea is that you get some probability of taking the first branch and some probability of taking the second branch. Now I have two distributions coming out of these two branches. I want to weight these distributions by what is the probability I win in the first branch versus what is the probability I win in the second branch. Okay, so if I had a very big probability of going in the first branch, then the first output distribution is going to have more weight because there's more mass there. If I have a very small probability of being in the first branch, then I kind of want to weight that distribution much less in the final output distribution. So we can think of kind of the if then else is kind of first conditioning a distribution into two parts, running both branches, and then blending them back together. Okay, so this is substantially more complicated than what we had for the monadic semantics, but it still hopefully represents some intuitive way of thinking about the probabilities. So, kind of putting everything together here, we're going to record the probability that the guard is true in the initial distribution. I'm going to call it P, and I'm going to say that there should be a mu here. Sorry. So the output distribution of if then else on a distribution is going to be the convex combination weighted by P of running the first command on the first conditional distribution and running the second command on the second conditional distribution. Okay, so I condition into two pieces, run both, and then blend them back together. Any questions about this?
I think you clarified it, but this P is computed by say I guess the law of total probability or some different.
So this P is just okay. So here I'm using some notation again where I'm saying you have input distribution mu, and E writes. So E is an expression. It maps every memory to either true or false. Okay, so by this notation, I'm saying in the initial distribution, what is the probability that E is equal to true? So I'm kind of viewing this thing here as a set here, kind of abusing notation, saying what is the probability that E is equal to true in the initial distribution. Yeah.
Okay, so you need to compute the probability of the guard separately.
Indeed. Indeed. Right. And all of this is kind of to emphasize again, like this doesn't give you a convenient or efficient or practical way of actually executing the program. Right. So this is just mathematically defining what is it supposed to mean. If you want to implement this, you would definitely not do this. Right. You would do something else. So like I'm not claiming here at all that's easy or feasible to compute this thing in practice. I'm just saying that mathematically that is what the number should be. And that is how we can define the semantics. But actually computing this stuff in reality is a completely different question.
Thanks.
Yep. Okay, so for loops, I'm mostly gonna just skip over, it's just probably don't want to get too much into kind of the gory details here. It's the same strategy as before for the monadic semantics, where we define these approximants. It's a little bit more complicated because now you have all this conditioning stuff going on and merging stuff together, because you can't just branch on whether the loop guard is true or false. But morally, things work kind of the same way, just with more ugly conditioning and convex combination. I'm gonna skip over that because I think we've had enough of loops. Okay, so I briefly want to give a quick comparison of the two semantics to say a bit more about these two things. So one kind of observation we can make is that you can convert the monadic semantics to the transformer semantics. So given any function from memories to distributions over memories, I can lift it to a transformer somehow that takes a distribution to a distribution by somehow averaging f over the input distribution. So I can define f lift here of an input distribution. And here m prime is kind of going to be the probability, it's going to be the memory I'm trying to get the probability of. So the probability of like seeing m prime in the output of f lift is going to be averaging over like mu of m, which is the probability of seeing m in the input, times f of m prime, which is the probability of seeing m prime in the output from m. So that was kind of a mouthful. But this is kind of a standard construction that doesn't really require anything about memories or anything else. So this is also known as the Kleisel lifting for the distribution monad. But it's a general construction that works for any sets here. So one thing you can kind of show is that you can kind of embed the monadic semantics into a transformer semantics, right? So we define the monadic semantics first, and if I lift it and I call it on input distribution mu, I'm going to get the same output distribution as if I just ran the transformer semantics on input distribution. Okay, so these two semantics are related in this way. Okay, so I think of this as kind of like a sanity check, right? So we have defined two semantics that say, you can plug in either a single input or distributional inputs. And it would be kind of strange if these two semantics gave different results if I plug in a distribution, right? It would somehow mean that the output of this program is not uniquely defined, like it was different in these two semantics, which would be kind of strange. Because I would expect like a program that can be the same output, right? At least if I feed it the same input under both semantics. However, you might wonder whether I can convert the transformer semantics to the monadic semantics in the other way, right? So unfortunately, this is not so, it's not so clean this way. So if I have a transformer, which maps distribution to distribution, there's not always going to be a map like this, such that f bar is f lift. So I can't always find a monadic semantics map that lifts to this transformer map. So the upshot of this, which is actually, which is quite fortunate, is that the transformer semantics can support more features than the monadic semantics, right? So we never saw any of this stuff because in PWHILE it doesn't make a difference. All of the features of PWHILE can be supported equally by both semantics. But most notably, if you want to add a conditioning instruction to your language, like in many probabilistic programming languages, then you actually need the transformer semantics, because the monadic semantics cannot express this kind of command anymore. You can't give a semantics of this with the semantics command, with the monadic semantics, which is a problem if you want to have this in your language. Okay. So that shows a little bit about the trade-off between these two things. All right, so yeah, I want to say a little bit more about for verification purposes, which is the focus of this course. Why should we prefer one or the other? Right. So the monadic semantics is nice for some reasons. One of the reasons is that assertions about single memories are simpler than assertions about distributions. Right. So a single memory is a simpler object than a distribution of memories. Right. So if I'm talking about a single memory, I can say x is bigger than 0, like x is less than 0. I don't have to think about probabilities or any of this stuff. If I'm talking about distribution of memories, then I can't just say x is 0 or x is bigger than 0. I can say the probability of this is something or the probability of that is something, but that's a more complicated assertion. Like suddenly you're quantitative. So as you kind of saw, like for certain things, it's convenient to kind of do a case analysis on the input memory, and for that, the monadic semantics is a good one to choose. That's can simplify verification. For the transformer semantics, you might want to use this because maybe you really want to assume some property of the input distribution. All right, so for monadic semantics, it doesn't make sense to assume some property of input distribution because there is no input distribution. It's just a single memory is the input. I can't talk about the probability of anything in input because there is no distribution there. There's just one memory, right? So, this can enable verifying kind of richer probabilistic properties. Okay. All right. Any questions about these two semantics before I continue? So I want to show a little bit about how to verify something with the transformer semantics. Before I get into that, maybe I'll stop it a bit and take questions.
Okay, there's a longer question in the chat here, but maybe you could quickly comment on the computational complexity of these two. Are they equivalent or?
I don't know much about the computational complexity of these things. Again, we don't really expect to actually compute these things in practice. They're mostly just for defining it mathematically what the program should mean. So yeah, I think I don't know much about the computational complexity, but the question in the chat is about transformer for if then else, feeling its way to renormalize, kind of dividing by p and then remultiplying by p. That's true. So yeah, so I kind of present the semantics in this way so that the input and output is always a full distribution, like something that sums up to weight 1. You can also present this in a way where you're transforming kind of sub-distributions. I think this is the way that probably Dexter Cozen originally did it in his paper. And I think, I'm trying to remember, then I think you might not need to renormalize like this. But I'd have to look at his paper again to see. Indeed. Okay, so I'm going to continue and kind of talk about a verification method that's based on the second semantics, this transformer semantics. To do that, I'm going to make like kind of a kind of big detour. So this kind of method is what we call a probabilistic separation logic. So I'm first going to introduce some bits about separation logic for non-probabilistic programs, and then show how this can be adjusted to handle probabilistic programs. But first of all, I want to talk about the property that we actually want to verify. Okay. So roughly, we want to verify like probabilistic independence. So if you haven't seen this before, we say that two random variables x and y are independent if they are not correlated. Right. So the value of x gives no information about the value or the distribution of y. Okay. So for instance, there's many things that are independent. So x is the result of a fair coin flip, and then y is the result of another fresh coin flip. Then x and y are kind of going to be independent. Now, there's also things that are kind of, that you might use for modeling that you expect x and y to be uncorrelated. So you're going to assume that they're independent, right? They're not coin flips, but you're assuming they're independent, right? So maybe x is today's winning lottery number, and then y is the closing price of today's stock market, right? You expect these x and y to be unrelated. So there's also stuff that's not independent, right? So if you kind of reuse a sample, you may end up with something that's not independent, right? So x is the result of a fair coin flip, fine. And then let's say y is the result of the same coin flip, like not a fresh coin flip, you just did the same thing, you got the same thing. Then x and y are intuitively not independent, because if I know what x is, then I definitely know what y is, right? Like knowing what x is gives me information about what y is going to be that I didn't have before. For modeling, you might expect two things to be not independent because they might have a common cause, right? So maybe x is today's ice cream sales and y is today's sunglasses sales. So these two things, you might want to assume they're not independent because they have a common cause, right? So if today is very, very hot, I expect x and y to both be very high. If today is very, very cold, I expect x and y to be very low, okay? So they're somehow correlated. So if you know what x is, then maybe you get some information about what the temperature is today, and then that will give you some suggestion that maybe y is going to also be high. Okay, cool. So what is independence formally? You can define independence as a property of a distribution. So I can say x and y are independent. If for all values a and b, I have this equality here. So the probability that x is equal to a and y is equal to b is equal to the probability of x equals a times the probability of y equals b. Okay, so in other words, kind of the distribution over the pair xy is the product of a distribution over x and a distribution over y. So if you've seen this before, then this seems very natural. If you haven't seen this before, I'm just going to claim that it's natural. This is the definition of independence, okay, for uncorrelated things. Okay, so why is independence useful? So I think of at least three reasons. So the first reason is that it's very common in probabilistic programs, right? So a fresh random sample is somehow, by definition, independent of the rest of the state. So it'd be useful if we have a way of reasoning about independence, because it comes up so often. Whenever you make a fresh sample, it's going to be independent. A second reason I think it's useful is that it really helps when reasoning about groups of variables. So if I have a bunch of variables, say 10 Boolean variables, if I know that if I have some general unknown distribution over them, then it can be very complicated. I can have very weird correlations where if the first two variables are true, then like the fifth variable is going to be false, or you have some weird, very weird correlation. However, if I know that all of these variables are independent, which again is often the case because every time I sample, I get an independent thing, then I know it's a product of distributions over each variable individually, right? So a distribution over one variable is much easier than a distribution over like 10 variables. So if I know it's independence, I know I can focus on each individual variable one at a time. And the third reason why independence I think is quite useful is that it's preserved under common program operations, right? So if I have a local operation that touches just a few of the random sampling results, I might transform it somehow to be something else, but it will remain independent of everything else that I didn't touch. Okay, so this is one, you have this kind of local kind of reasoning where it's preserved. If I don't touch other samples, then it will remain independent. Another reason is that another useful kind of application is that independence behaves well under conditioning. So if I condition something, condition distribution, then the part that is independent of what I'm conditioning on is going to be preserved. So I know that whatever was true there before is still going to be true after conditioning. And as we kind of saw in the if then else stuff, for this transformer semantics, we are going to be conditioning on the distribution quite often whenever you have probabilistic control flow. Okay, so these are just three like motivating reasons. However, the problem like for verification is that the formal definition isn't very promising because you have this quantification over all the values, so you have all these probabilities, and kind of computing all of those probabilities like manually, say using the weakest pre-expectation calculus or whatever, is very tedious and can be very difficult, right? So like what this kind of system we're going to present is going to try to do is to leverage the intuition behind independence to reason about this in a kind of a lightweight way. Okay, so maybe I kind of skip over some of this stuff because it's not so interesting. I mean, where we're going to go is that we wanted to develop a separation logic to reason about independence, and a separation logic was already developed by Peter O'Hearn, John Reynolds, and Han-Sok Yang in a different context for reasoning about programs that manipulate memory and heaps and pointers, so with nothing to do with probabilities. But we can see by kind of tweaking the definition or tweaking the interpretation of what the logic means, we can kind of adapt it to talk about probabilistic independence as well. Okay. All right, so I want to kind of give a high-level view of what is going into a separation logic to see the ingredients that we're going to use. Okay, so from my perspective, there's kind of three ingredients in a separation logic. So first, there's a kind of program, right? So programs are going to transform input states to output states. And for our purposes, we're going to use PWHILE with the transformer semantics, because a PWHILE program takes input distribution to another output distribution. It transforms the state to another state. Okay, so the first one is easy. We've already done that. The second thing you need in separation logic is that you need assertions to describe program states, which for us are going to be distributions over memories. So the logic that's used in separation logic for these assertions is called BI, which is called a logic of a bunch implications. I'll talk about it a little bit next. And the semantics, which defines, which formulas are true and which distributions, is defined by kind of a model of BI, which I'm going to introduce next. And finally, there's kind of the program logic proper, right? So the program logic is going to have the judgments are going to have precondition, which is going to be an assertion, a program, which is drawn from the first part, and then a postcondition, which is another assertion. Okay, so we have programs, then we have assertions talking about distributions, and then we have the program logic, which talks about programs themselves. Okay, so we have these kind of three pieces that we're going to do. The first one we've already done, so that's fine. So I'm going to talk mostly about the second one and the third one. Okay. Okay, so I wanted to quickly go over, some of, standard separation logic without probabilistic programs, again, trying to motivate, where all the stuff comes from and, what are the things we need to change to make it work for probabilistic programs. So in the classical setting is for kind of heap manipulating programs. There are no probabilities. There's just a program that can manipulate pointers and memory. Okay, so the program state is a pair of a store and a heap. So the store maps every program variable to a value, and the heap you can think of as a piece of memory, right? So it's a partial map from addresses to values. So a natural number is some address, and then if it's allocated, you have a value there. If it's not allocated, you'll have nothing there. Okay, so it's like a memory, like a heap, like you might expect. And the programs themselves manipulate these pairs, right? They take a pair of a store and a heap to a new pair of a store and a heap. And when the programs are executed, they can do stuff like, assignment, sequencing if then-else loops, but they can also do stuff like reading and writing addresses in the heap, or allocating and freeing heap cells, like saying, I want a new location in the heap and I don't want to allocate it, or I want to free this location and remove it. Okay. So the assertion logic that's kind of Peter O'Hearn and David Pym developed to kind of talk about these program states, say pairs of stack and a heap, is called a logic of bunch implications, BI. So the idea is that this kind of logic has the regular pieces of logic, like you have true, false, and or implication. And you add two things, right? You add something called star, which is another kind of conjunction. It's like another kind of and you add a new implication called magic wand, okay, which looks like this. It's really called magic wand. And so the idea is that star and are both conjunctions. So they say that P and Q are true, but they behave a little bit differently. Right? So P and Q, P like and Q, that's the regular meaning of P and Q. It says P and Q both hold on the entire state. P star Q says a little bit, means a little bit different. It says P and Q hold on disjoint parts of the state. So that somehow this state that you have can be split into two separate parts, and P holds on the first part and Q holds on the second part. It's not that they hold on the whole thing together. It's that you can split the state into two separate parts where P holds and where Q holds. Okay. So I want to quickly talk about, how you can define the semantics of BI for, in general. So the main thing you need is that you need the program states that form a preordered and partial monoid. So there's a set of states S, which can be stacks and heaps, or it can be distributions over memories or whatever. There's a preorder on S, which let's just forget about that for now. And there's a partial operation that takes two states and might give you another state back, or might not. It might not be defined. Okay, and it's associative, commutative, and all of this with respect to dealing with the partiality stuff. And then given this kind of structure, you can inductively define, which states are true in which formulas. So here, these things are really a definition where I'm saying, let me back up here. I'm saying state S holds in, the formula true holds in state S. That's how you should read it, it's always. The formula bottom, which means false, holds in state S, never. The formula P and Q holds in state S if P holds in S and Q holds in S. And finally, the most interesting one is that the formula P star Q holds in S if I can split S into two parts, S1 and S2, such that P holds in S1 and Q holds in S2. Okay, so this says that, P star Q holds in S if I can split S into two parts, where P holds and then where Q holds.
Okay, I think you just answered that, but with the star, it has to form a partition, or can there be parts of the state where neither of these things hold?
Well, okay, so here I've written, so everything here, like, because we're in a very general setting of just having a monoid, there's really not a notion of a partition exactly, right? It's like, I'm not partitioning the states, right? So when when S1 circle S2 is less than S, it means that I can think about it as saying inside S, I can split a part of it into S1 and S2. Okay, so this preorder, like if you imagine this to be equality, it would say you have to split the whole state. If it's not equality, you could think about it as kind of being some kind of subset, maybe like, I have a smaller state inside my bigger state, and I split that smaller state into two parts. So maybe this is sort of answering the question.
If not, maybe you could reply, David. But Chuta has two questions. Is this related to relevance logic, and is the exchange implicit?
Yes, so it is related to relevance logic. It's also, you can kind of think about it as related to linear logic as well, though again, it's kind of different. I'm looking at more exchange is implicit. So exchange, because it depends on what you mean by exchange, right? So we do think that star is going to be commutative. So P star Q implies Q star P and so on, and associative and everything. Right. So you have exchange in that sense. So there's a question about whether there's a modal logic formulation. So this is kind of a modal logic formulation. So you can think about BI as a modal logic, right? So you have a set of worlds or states, and certain formulas are true in certain worlds. And this is the Kripke semantics. Right? The only twist here is that there's kind of this partial operation on worlds, which you often don't see in a modal logic, but you can put there as well. And that represents splitting and separation. Can S1 and S2 have intersection that's non-empty? So far what I've said here, like S1 and S2, like it might not even make sense to, like none of this definition talks about intersection or union of S1 and S2, right? The only thing we have is combining it using a circle, right? So depending on how you define circle, you can allow S1 and S2 to have some overlap, or you can say S1 and S2 are only defined to be combinable when they have no overlap, but you can choose how you want to define this. It's all depending on how you define the circle operation. Right? Like a priori, there's no intersection or union inside this semantics. It's not nowhere to be seen here, right? Yes. Okay. I'm gonna continue and kind of show a concrete example of the heap model for BI. This is again for heaps, for no probabilistic stuff, just for programs that manipulate pointers and variables. So here, I've dropped the kind of store to simplify things a bit, but let's say that a set of states is going to be heaps. So each heap is going to be a map from natural numbers to values. It's going to be a partial map. So you can think about this as a piece of memory, right? So each address is either allocated and there's a value there, or it's not allocated and there's nothing there. Okay. So the mono operation we want to take is to kind of combines disjoint heaps. So I'm going to say that S1 circ S2 is defined to be the union of these two heaps, if and only if the two heaps have disjoint domains, right? So imagine I have two heaps, and I'm saying these two heaps, if these two heaps are defined on different addresses, right? So there's no address that's defined in both heaps. Then if this is the case, then I can combine these two heaps by making like a union a heap, right? So a heap where, all the addresses that are defined in the first heap or the second heap are defined in this combined thing, and the values are given by, the original heaps. Okay. Right. So in some sense, this is kind of backwards from how you might think about separation logic. So often you would think that, oh, like two things are separate. Like if I can take this state and split it into two pieces that are separate. So I want to define when can I split a state into two things that are separate. So this mono operation is kind of in the reverse direction of intuition, which says that S1 and S2 can be combined if they are separate, right? So this, you're still defining when things are separate, but you're defining it like when can stuff be combined together, and if stuff can be combined, then they are separate somehow, like that. And the preorder, which I was mostly not talking about, is kind of extend or project heaps, right? So you can kind of read the preorder as saying, S1 is less than S2 if S1 has less information than S2. So if S1 is a heap and S2 is another heap that allocates strictly more addresses, and furthermore, the two heaps agree on everywhere in S1, then S1 is less than S2. So you kind of get S1 by taking S2 and throwing away some of the stuff that's been allocated, and then that's S1. So, with just these kind of ingredients, this is going to give a model of BI. So then you can kind of define what it means for and to be true and star to be true, and so on and so forth, as in the previous slide. Okay. And finally, we want to talk about heaps, and we want to say, we want to say like, we want to have some assertions about heaps and, whether they're satisfied assertion or not, right? So the typical atomic assertions you take in separation logic for heaps look like something like this. X points to V. This is how you read X points to V. So X points to V holds in a heap S if kind of X is allocated. So X is in the domain of S. So the heap talks about X. And furthermore, S of X is equal to V. So if you look up what is at location X in the heap, you'll get the value V. Okay, so clearly this could be true or false depending on what kind of heap you have. But it might be true or might be false. And typically along with these propositions, you'll have kind of axioms about these things. Of course, these are not a complete set of axioms, but for instance, you might say that if X points to V and Y points to W, and X is equal to Y, then I know that V is equal to W. Right? So kind of the heap is deterministic because if I have two of the same addresses, two addresses are the same, and then I know that they must point to the same thing. They must hold the same value in memory because of the same address. I can also have stuff like where I have disjoint properties where, if X points to V and separately Y points to W, then I know that X and Y must be different addresses because the star says I can split the heap into two separate parts with different domains, where X is holding in the first part and Y is holding in the second part. So X and Y can't be the same address because I know that they're separate using star. Okay. Any questions about this before I go on? Okay, so we have heaps, we have assertions about heaps, and we have different ways of kind of combining these assertions. Then kind of the separation logic proper, which is the part we've talked about assertions. Now we talk about the separation logic, which talks about the programs. This kind of stuff works with kind of programs that can manipulate pointers. So you can imagine a programming language where you have two commands. One is for reading from a pointer, dereferencing a pointer and storing to a variable. Another one is writing to a location, right? So you dereference a pointer and you store something into that location in the heap. And then your program logic will try to prove things of this form, where it says that if the assertion P holds an input heap, then when you run C, you will get an output heap that satisfies Q. And furthermore, C is not going to make any kind of memory errors. So running C is not going to read or write to invalid memory or heap locations. So this is this kind of the guarantee you have by proving these kind of judgments. Okay.
There's a question about the magic wand operator.
Magic wand, yeah. So I skipped magic wand. Yeah, I can talk to you more about magic wand later if you're curious. It's a little bit harder to understand. It's related kind of as an adjoint to the star, but the interpretation is a little bit confusing. It can also be quite useful for reasoning about heap manipulating programs. But I think thinking about just the star conjunction is probably enough for now. Yeah. Okay. Great. Okay. So we want to take that kind of thing I sketched before for heaps and programs that manipulate heaps, and I want to develop a probabilistic model of BI in order to kind of talk about probabilistic programs. So the upshot of all of this is that we're going to try to reuse the star, which used to talk about separate heap locations. We're going to try to reuse that star to talk about probabilistic independent parts of the distribution. So I want to say that X and Y are independent if X star Y holds. So how do we kind of put this all together? So the first change we have is that we're working with probabilistic programs under this transformer semantics. So the states are going to be distributions over memories. There's not going to be the stack and heap stuff anymore. There's going to be a distribution over memories, like we saw before. Oops. So the memories. Okay, forget about this. So I'm going to say I have a set of variables X and a set of values V. We saw it before. And each, I can consider memories to be indexed by domain. So I can talk about a memory that mentions some of the variables, but not other variables. So M of A is going to be maps from A to values. It assigns every variable in A a value V. So you can imagine these as kind of partial memories. So a memory maps every single variable to a value. M of A only maps the variables in A to a value. Okay, and then the program states we have are kind of going to be randomized memories, right? So, states are kind of distributions over memories with the same domain. Formulate something like this. And, I can have a distribution over a memory that only mentions some of the variables. I'm trying to see if there's more questions in the chat. Yes. Yeah, BI has a bunch of implications, which is not a great name for the logic. But yeah. Okay. So kind of the heart of this model, kind of saying which, we want to show, essentially we want to say which formulas are true in which distributions over memories. We want to define when a formula is true in a distribution over memories. This way we can use these assertions to talk about distributions over memories. So we can use them as pre and post conditions for the program logic. So the main kind of operation we want is, we want this kind of partial monoid operation, which takes two distributions over memories and combines them possibly into a single distribution over memories. The intuition that we want to use is that two distributions can be safely combined if they are talking about different variables. And to combine two distributions, I'm going to take the product distribution and then union the domains. So it looks something like this. So suppose I have a distribution over memories over variables A, and another distribution over memories over variables B. Then if A and B are disjoint, so they talk about different variables, there's no variable that's talked about by both of these distributions, then I'm going to define the combined distribution, S circ S prime, to just be S of M, which is the first probability, times S prime of M prime, which is the second probability. So essentially, I'm building the product distribution out of two distributions that are talking about different variables. Okay, so if these two distributions talk about the same variables or they share a variable, then I'm going to say that S circle S prime is not defined. So I cannot safely combine these two distributions. Okay, so the kind of upshot of this is that if I have a distribution where I can say it's equal to S circle S prime, then I know it must be that I can split this single distribution into an independent product of two distributions. And then I know that the two parts are going to be independent. And I can talk about independence here. Does this make sense? Okay, gonna continue a little bit more and then I think I'm probably out of time for today. So preorder is, like I said, one way of reading this preorder is to say that, S is less than S prime if S has less information than S prime. So what we're going to define this preorder to be is that we have a bigger distribution, which talks about maybe a bunch of variables in B, and I have a smaller distribution, which talks about variables in A, which is a subset of B. Then I can obtain the smaller distribution by kind of marginalizing or projecting out, kind of forgetting all of the distribution of variables that are not in the smaller set. So in probabilistic cases, it's kind of like a projection or a marginalization. Here, you can kind of, this is kind of an ugly formula, but the idea is that you kind of forget all the information about certain variables in your distribution. You just say, I have a distribution over a bunch of variables. I just want to consider the distribution over these fewer variables by forgetting everything else. Again, some maybe kind of confusing about why you'd want to choose. I mean, in these parts, these choices may look very arbitrary, like why should we choose the preorder to be this way, or why should we choose the combination operation on the previous slide to be that way. But these are kind of natural operations on distributions, and it turns out that everything behaves very well if you use these things. Right? So if you want to say that one distribution has less information than the other, one natural way is to say I can marginalize the bigger distribution to the smaller one by forgetting a bunch of information. And likewise, if I have two distributions I want to combine into one distribution, one natural way is to say I take the independent product to make a single distribution where these two things are independent. Okay. So this kind of defines the model of BI. So with this, different assertions in BI can talk about distributions over memories, and you can talk about whether things are separate or not separate. So let me see, one more ingredient we want to add is we want to talk about specific distributions, right? So we want to add atomic formulas which talk about, these are the analog of this, X points to V kind of assertion. We want to talk about stuff that holds in a distribution or not, right? So one thing we can add is a kind of inequality. So I'm going to say that, E is equal to E prime. This is an assertion. This is going to hold in a distribution S if all of the variables in E and E prime are defined by the distribution. So the distribution kind of says, what is the probability of all of these variables? And furthermore, E is equal to E prime with probability 1 in the whole distribution. So whenever you draw from this distribution S, you will always see that E is equal to E prime. Okay. So this is one assertion we want to have about our distribution. We can also add other kinds of assertions. So one that you can add is that you can say an expression is uniform. So here I have this assertion, uniform subscript S of E, and this says that first of all of the variables in E must be inside a distribution, so they're defined, and furthermore E is uniform distributed on the set big S. So for instance, if big S is Boolean, this says that E is a uniform Boolean. Okay, it's 50% true and 50% false. We can also introduce this other kind of assertion here, which the purpose is maybe a little bit less clear right now, but this just says that this thing says that all of the variables mentioned by E are inside the distribution, that the distribution gives a probability to all of the variables inside E. Okay. Let me see if there's any questions. Any questions?
I guess
yeah, go ahead.
Maybe to clarify a little bit for my benefit. So normally when you have like a dependence graph, whether it's a computational graph or like a graphical model, you kind of look at the provenance of the variables. And you're saying here that kind of, if I understand correctly, you want to prove the independence or separation of different variables, and maybe in many cases you might not have that whole provenance. So do you have to test? Do you have to test this these conditions hold, or how do you go about establishing like the base case?
Right. So that's a good question. So far what we've kind of discussed here is just talking about formulas that talk about, assertions that talk about distributions over memories. Okay, so the programs themselves have not really entered the picture yet. So everything we have here just says, given some distribution over memories, which is a program state, when is this assertion true or not true? I'm kind of defining that. I'm saying like E is equal to E prime is in this distribution if blah, blah, blah. Okay, and unif E holds if E is uniform in this distribution. But there's no notion of program yet, right? So the next step, which I'll probably get to next time, is what I call the program logic proper. So this is just the logic of assertions. And the program logic proves kind of these triples, these Hoare triples, where you have an assertion, which is a precondition, then a program, a PWHILE program, and then another assertion, which is the postcondition Q. Okay, so when we get to that part, we'll be able to prove stuff about programs themselves, saying if the initial state satisfies this kind of condition, then when you run the program, the final state is going to satisfy this other kind of condition. Okay, but so far we're not there yet. So we're just trying to define what does it mean for a state to satisfy a condition first, without even thinking about transforming it or anything.
That helps. Yeah, thanks. I kind of see where we're going.
Yeah. Okay, so I think I'm pretty much out of time. I think I probably better stop here. Next time I'll kind of pick up here and kind of continue talking about this program logic, and then in whatever remaining time I have, I'll switch to the last bit of the course, which is talking about higher order programs. Okay, cool. Thanks everyone. I'll be around for a few more minutes if you have any questions.
Great, thanks, Justin. So yeah, if anyone has some more questions, we can ask those now. Otherwise, we can wrap up.
There's a few good ones in the chat. Do you want me to read them? Or
yeah, please.
See, can the distributions be defined over complex spaces like the space of all possible binary trees? So far, right. So for our purposes here, we're going to be using these assertions to talk about program states, right? So, and for us, program states will be distributions over memories. In general, you could define this kind of model to talk about other kinds of distributions, but for our purpose of developing a program logic, we just need the assertion to talk about program states, so distributions over memories. Okay. The second question is, if the semantics define only from a mathematical notation, How does this translate to an implementation of an interpreter for the language? I'm curious to understand how the reasoning is handled in practice. Yeah, this is a good question as well. So there's many purposes of defining a semantics for a language. So one reason, I guess, which is common in language design, you're designing a language, you give it a semantics, and then from the semantics you can build like an interpreter, or you can extract out an implementation of this of the language. You might want to do this because you say, you know, I've defined it mathematically what semantics is. Now I want to have an implementation of that can execute programs. It might be very, very slow, or or not very practical, but I have at least one implementation I can compare against other faster implementations of my language. Right? So that's a common reason to define language semantics for language design. For verification purposes, our goals are a little bit different, right? So I think the goal here is not to develop an interpreter or a compiler or something for probabilistic languages. So the only goal here, the main goal here is I want to define the semantics so that I can show that a certain verification method is sound with respect to the semantics. Right? So the semantics defines a program behavior, and I want to say that if my verification method says yes, that means the program behavior must do this, must be this. Okay, so the interest here is not so much finding a reference implementation of the PWHILE language or something like this. It's more like defining what it means for a verification to be correct, I think. Does that make sense?
Yeah, I think that makes sense. You're more interested in kind of proving maybe properties of the semantics or the reference implementation rather than implementing the probabilistic programming language.
Indeed, yeah. Question, what is the meaning of having a bug in probabilistic programs? Can we identify a bug from the output? For instance, if a probabilistic program computes a distribution, do we sample the distribution? Right, so at this, so the purpose, like in all kind of verification, the meaning of having a bug depends on what property you want your program to enjoy, right? So at a very rough level, you can say, a program has a bug if it can crash, okay? Because crashing is clearly a bug. But you might have other bugs that are, not crashing the program that you still care about, right? So for, security like cryptographic applications, maybe like if this encryption scheme does not satisfy this probabilistic property, then it has a bug. It doesn't crash, but it leaks information to the adversary or whatever. And it doesn't accomplish what it's supposed to accomplish, right? So the meaning of having a bug is, you can say like, I want my program to satisfy property P, which maybe means the crypto protocol is secure or the machine learning algorithm converges or whatever. And if it doesn't do that, then it has a bug, right? So can we identify a bug from the output? This is also a good question. So for probabilistic programs, you typically, many interesting properties of probabilistic programs, you cannot identify a bug from the output. Because when you run the program, you just see one sample. And you might not know like whether or not, like, did you just get unlucky that you got kind of a bad sample? Or, because your property is talking about the distribution of values of your output, but you don't see the whole distribution, right? You just see one sample. Right? So if your probabilistic program has a bug, it can be quite difficult to actually identify it by running the program, because you don't know simply whether you just got unlucky or whether the distribution is wrong. So this can be difficult. Can you use probabilistic reasoning to show computational soundness? I'm not sure what computational soundness means here, but maybe you can clarify.
Hi, yeah, it's used in cryptography. Basically, it means that this program is correct as long as my adversary doesn't have a supercomputer that can prove exponential programs in polynomial time. Sure.
Yeah, so indeed, there's a lot of work on, well, not a lot of work, but there's been a few very successful lines of work on proving, let me see if I can back up, proving security of cryptographic protocols under a computational assumption. So you would like to say that assuming this problem is hard, like no adversary can, invert a one-way hash function, then no adversary can break the soundness of my cryptographic scheme. So there's a lot of work. I would encourage you to look at work on probabilistic relational Hoare logic, so PRHL. So a lot of the work by Gilles Barth's group over many, many years. They developed kind of program logics and Hoare logics to reason about kind of reduction-based security, saying like, if you can win against one program, then you can win against another program. And by building up a chain of these things, you can say that assuming no one can win against this simple program, that means my original program must have been secure because I can't have reduced them like this. It's a very interesting area of work because you're kind of reasoning about relations between pairs of probabilistic programs that are not the same. And you want to show somehow that there are computationally indistinguishable, maybe they're approximately giving the same distribution. But there has been a lot of really interesting work done on that side that I would encourage you to look into if you're curious. Okay, yes, PRHL, probabilistic relational Hoare logic, yes. This is, yeah. There's a lot that's been written on it, I think. Okay, any other questions? Let me click the link. Yes, this one, but yeah, this is probably the first work, I think. But there are probably longer articles about this. This is only 5 pages, I think. There are some conference articles about this as well.